Okay, so we're continuing our conversation about what happens in mixtures of acids and bases. And today we're going to be talking about how the pH of the solution can be used to tell us what is going to be more prevalent, the acidic form of a weak acid or base or the basic form of a weak acid or base. So let's jump right in and talk about the pH and the species that are present in a mixture. So really what we're going to be focused on today is what's in our solution. So if we have a solution of a weak acid or base, we know, because it's at equilibrium, that the acid and the conjugate are both present, or the base and its conjugate are both present. But how do we know which one we have more of? Well, if there's nothing else going on, then we know that it's all governed by Ka or Kb. So since we know that Ka and Kb are both going to be affected by pH, let's talk about pH. So if our pH, if we're talking about a weak acid, if the pH is below pKa, that means we're going to have more weak acid and less conjugate base present. If the pH is above the pKa, then we're going to have more of the conjugate base and less of the weak acid. By the same token, if we're talking about a solution of a weak base, if the pH is above the pKb, then we're going to have more of the base. And if the pH is below the pKb, then we're going to have more of the conjugate acid. So this is really a pretty simple and straightforward application. If you think about what's going on in a titration, when we talked about our weak acid titration with a strong base, you know that at pH, when pH is equal to pKa, we have equal quantities of weak acid and conjugate base. Once the pH gets above pKa, we have more conjugate base. When the pH is still below the pKa, we have more of the weak acid. So let's do a quick exercise. So our student pours a 10 milliliter sample. This sample contains both acetic acid and sodium acetate. So we know that we have both the acid and its conjugate base. Now we add an indicator. We add bromocresol green to the test tube and we see a yellow color. And that yellow color tells us that the pH of the solution is less than 3.8. So since our solution is at a pH lower than our pKa, what are we going to have more of? We just said that if we have a pH below the pKa, we're going to have more of the acidic form. And so that tells us that we're going to have more acetic acid than sodium acetate. And so A is our answer. Okay, so a practical application of this idea that pH and pKa are related is the use of indicators. And we've already talked about acid-base indicators when we talked about titrations. And we said that they are generally large organic molecules that have both an acidic and a basic form. So they're either weak acids or weak bases. So they're just weak acids or bases that have a different color in their protonated and deprotonated forms, so in their acidic form and their basic form. So we can use these because if we are above their pKa, we're going to see their basic form. So we'll see the color associated with the basic form. If we're below the pKa, then we're going to see the acidic form and we'll see the color associated with that acidic form. Now, limitations in human perception mean that in order for the color change to be visible, there has to be a pH change of approximately 1 unit. So 1 pH unit, and remember the pH scale is a logarithmic scale, so a 1 unit change means that there's a 10-fold change in the concentration of acid or base. So what does that mean for us? It means that indicators usually change color at their pKa plus or minus 1. So when pH is plus or minus 1 of the pKa, that's where the indicators usually change color. And so that allows us, if we know that there's a color change, to determine what the pKa of that weak acid is. It also allows us to choose the appropriate indicator for our titration. So a little practice. We have the acid-base indicator, cresol purple. So cresol purple is yellow if the pH is below 7, and it's purple when the pH is above 9. So knowing what you know about pH, what you know about indicators, what you know about pKa values, can we predict the pKa of cresol purple? Well, we know that an indicator changes at plus or minus 1 pH unit of its pKa. So that tells me that the pKa of cresol purple must be 8. All right, and last practice, we have a titration curve here, and we're asked to determine what's the best indicator. So we want to choose an indicator for our titration where the equivalence point is in the middle of the indicator's pH change range. And so we're going to look at our graph and we can see that this changes somewhere below 9. It's not quite halfway in between the 8 and 10, so maybe around 8.8. And so we're looking for something that has a color change or a pKa somewhere around 8.8. And we can see that methyl orange and methyl red, as well as bromethymol, all change color far too low. They would change way down here before we ever reach that equivalence point, or even over here. Phenolphthalein, on the other hand, changes color between 8.2 and 10.0. So that looks like a good choice. We'll just take a quick check. So alizarin would change too late. Alizarin wouldn't change until here. And so phenolphthalein is our best choice. So that's it for understanding how pH impacts the structure of these molecules. As always, if you have any questions, let me know.